Welcome friends. In this module, we discuss solution of equations, bisection method and Regula Falsi method. Solution of equation. Consider a mathematical equation in x of the form f of x equal to 0. A solution of the equation f of x equal to 0 is a value a such that f of a equal to 0. In other words, a solution of an equation is the value of the variable that makes the equation a true statement. In that case, the value a is also called 0 or root of the function f of x. For example, consider the equation f of x equal to x square minus 3x plus 2 equal to 0. A equal to 1 is a solution because f of a equal to a square minus 3a plus 2, that is equal to 1 square minus 3 into 1 plus 2 equal to 0. B equal to 2 is a solution because f of b equal to b square minus 3b plus 2, that is equal to 2 square minus 3 into 2 plus 2 equal to 0. Hence, 1 and 2 are the zeros or roots of f of x. An equation f of x equal to 0 is called an algebraic equation if the corresponding f of x is a polynomial. An example is x square minus 3x plus 2 equal to 0. F of x equal to 0 is called transcendental equation if the function f of x contains trigonometric, exponential or logarithmic functions. Some examples of transcendental equations are the following: sin x minus 0.5x equal to 0, ax square plus log of x minus 3 plus e raised to x sin x equal to 0. A formula for the roots x1, x2 of a quadratic equation ax square plus bx plus c equal to 0 is x1 equal to 1 by 2a into minus b plus root of b square minus 4ac and x2 equal to 1 by 2a into minus b minus root of b square minus 4ac. Consider the equations a, x square plus 4x plus 2 equal to 0 and b, x square minus 40x plus 2 equal to 0. For the equation in A, formula gives roots rounded to 3 decimal places as x1 equal to 2 plus square root of 2, that is equal to 2 plus 1.414, that is equal to 3.414. x2 equal to 2 minus square root of 2, that is equal to 2 minus 1.414, that is equal to 0.586. And for the equation in B, we have x1 equal to 20 plus square root of 398, that is equal to 20 plus 19.950, that is equal to 39.950. x2 equal to 20 minus square root of 398, that is equal to 20 minus 19.950, that is equal to 0.050. Solutions of equations so obtained using mathematical formula are sometimes called exact solution or exact roots. Formula that give exact solution or exact roots will exist only in very simple cases. Equations like e raised to x minus 4x equal to 0 cannot be solved algebraically to find exact roots. Hence, in most cases, we have to use approximation methods, in particular numerical iteration method for solving equations for a near approximation of the solutions. A numerical iteration method or simply iteration method is a mathematical procedure that generates a sequence of improving approximate solutions for a class of problems. A specific way of implementation of an iteration method, including the termination criteria, is called an algorithm of the iteration method. In the problems of finding the solution of an equation, an iteration method uses an initial guess to generate successive approximations to the solution. Since the iteration methods involves repetition of the same process many times, computers can act well for finding solutions of equation numerically. Some of the iteration methods for finding solutions of equations are bisection method, method of false position or Regula Falsi method, Newton's method and secant method. In this session, we describe bisection method and method of false position. A numerical method to solve equations may be a long process in some cases. If the method leads to value close to the exact solution, then we say that the method is convergent. Otherwise, the method is said to be divergent. Bisection method. The bisection method is one of the bracketing methods for finding roots of an equation. For a given function f of x, guess an interval which might contain a root and perform a number of iterations where in each iteration the interval containing the root is get halved. The bisection method is based on the intermediate value theorem for continuous functions. If f is a continuous function and f of a and f of b have opposite signs, then at least one root lies in between a and b. If the interval ab is small enough, it is likely to contain a single root. That is, an interval ab must contain a root of a continuous function f if the product f of a into f of b less than 0. Geometrically, this means that if f of a into f of b less than 0, then the curve f has to cross the x-axis at some point in between a and b. See figure 1. Algorithm for the bisection method. Suppose you want to find the solution to the equation f of x equal to 0 where f is continuous. Given a function f of x continuous on an interval a0, b0 and satisfying f of a0 into f of b0 less than 0 for n equal to 0, 1, 2, etc. until termination, do compute xn equal to 1 by 2 into an plus bn. For example, see figure 1a for x0. If f of xn equal to 0, accept xn as a solution and stop, else continue. If f of an into f of xn less than 0, a root lies in the interval an xn. Set an plus 1 equal to an and bn plus 1 equal to xn. If f of an into f of xn greater than 0, a root lies in the interval xn bn. Set an plus 1 equal to xn and bn plus 1 equal to bn. Then f of x equal to 0 for some x in an plus 1 bn plus 1. Test the criteria for termination. Criteria for termination. A convenient criterion is to compute the percentage error epsilon r defined by epsilon r equal to modulus of x r dash minus x r divided by x r dash into 100%, where x r dash is the new value of x r. The computations can be terminated when epsilon r becomes less than a prescribed tolerance, say epsilon p. In addition, the maximum number of iterations may also be specified in advance. Some other termination criteria are as follows. Termination after n steps, n given and fixed. Termination if modulus of x n plus 1 minus xn less than or equal to epsilon, epsilon greater than 0 which is given. Termination if modulus of f of xn less than or equal to alpha for alpha greater than 0 which is given. In this session, our criterion for termination is terminate the iteration process after some finite steps. However, we note that this is generally not advisable as the steps may not be sufficient to get an approximate solution. Example 1. Find a real root of the equation f of x equal to x cube minus x minus 1 equal to 0. Solution. Step 1. Since f of 1 is negative and f of 2 is positive, a root lies between 1 and 2 and therefore we take x0 equal to 1 plus 2 divided by 2, that is 3 by 2, that is 1.5. Step 2. F of x0, that is 27 by 8 minus 3 by 2, that is 15 by 8 is a positive and hence f of 1 into f of 1.5 less than 0 and hence the root lies between 1 and 1.5 and we obtain x1 equal to 1 plus 1.5 by 2, that is 1.25. Step 3. F of x1 equal to minus 19 by 64 which is negative and hence f of 1 into f of 1.25 greater than 0 and hence a root lies between 1.25 and 1.5. Hence x2 equal to 1.25 plus 1.5 divided by 2, that is 1.375. Step 4. The procedure is repeated and the successive approximations are x3 equal to 1.3125, x4 equal to 1.34375, x5 equal to 1.328125, etc. Example 2. Find a positive root of the equation x e raised to x equal to 1 which lies between 0 and 1. Solution. Step 1. Let f of x equal to x e raised to x minus 1. Since f of 0 equal to minus 1 and f of 1 equal to 1.718, it follows that a root lies between 0 and 1. Thus, x0 equal to 0 plus 1 by 2, that is 0.5. Step 2. Since f of 0.5 is negative, it follows that a root lies between 0.5 and 1. Hence, the new root is 0.75. That is x1 equal to 0.5 plus 1 divided by 2, that is 0.75. Step 3. Since f of x1 is positive, a root lies between 0.5 and 0.75. Hence, x2 equal to 0.5 plus 0.75 divided by 2, that is 0.625. Step 4. Since f of x2 is positive, a root lies between 0.5 and 0.625. Hence, x3 equal to 0.5 plus 0.625 by 2, that is 0.5625. Since the difference between the last two approximations is very small, we accept 0.5625 as an approximate root. If more accuracy requires, go for some more iterations. Example 3. Solve x cube minus 9x plus 1 equal to 0. For the root between x equal to 2 and x equal to 4 by bisection method. Solution. Given f of x equal to x cube minus 9x plus 1, now f of 2 equal to minus 9 and f of 4 equal to 29. So that f of 2 into f of 4 less than 0, and hence a root lies between 2 and 4. Step 1. Set a0 equal to 2 and b0 equal to 4, then x0 equal to 2 plus 4 by 2, that is equal to 3, and f of x0 equal to f of 3, that is equal to 1. Step 2. Since f of 2 into f of 3 less than 0, a root lies between 2 and 3, then x1 equal to 2 plus 3 by 2, that is 2.5, and f of x1 equal to f of 2.5, that is equal to minus 5.875. Step 3. Since f of 2 into f of 2.5 greater than 0, a root lies between 2.5 and 3, then x2 equal to 2.5 plus 3 divided by 2, that is 2.75, and f of x2 equal to f of 2.75, that is minus 2.9531. Step 4. Since f of 2.5 into f of 2.75 greater than 0, a root lies between 2.75 and 3, then x3 equal to 2.75 plus 3 divided by 2, that is 2.875, and f of x3 equal to f of 2.875, that is minus 1.111328. Step 5. Since f of 2.75 into f of 2.875 greater than 0, a root lies between 2.875 and 3, then x4 equal to 2.875 plus 3 by 2, that is 2.9375, and f of x4 equal to f of 2.9375, that is minus 0.09008. The steps are illustrated in the following table. We accept 2.9375 as an approximate solution of f of x, since f of 2.9375 equal to minus 0.0901, approximately 0. Merits of bisection method. The iteration using bisection method always produces a root, since the method brackets the root between two values. As iterations are conducted, the length of the interval gets halved. So one can guarantee the convergence in case of the solution of the equation. The bisection method is simple to program in a computer. Demerits of bisection method. The convergence of the bisection method is slow, as it is simply based on halving the interval. Bisection method cannot be applied over an interval where there is a discontinuity. Bisection method cannot be applied over an interval where the function takes always values of the same sign. The method fails to determine complex roots. If one of the initial guesses a0 or b0 is closer to the exact solution, it will take a larger number of iterations to reach the root. Regula Falsi method or method of false position. This method is also based on the intermediate value theorem. In this method also, as in bisection method, we choose 2 points an and bn such that f of an and f of bn are of opposite signs, that is f of an into f of bn less than 0, then intermediate value theorem suggests that a0 of f lies in between an and bn if f is a continuous function. To find a real root of f of x equal to 0 using Regula Falsi method, we replace the part of the curve between the points an f of an and bn f of bn by a chord, that is straight line joining the 2 points a and b, see figure 2, in that interval, and we take the point of intersection of this chord with the x-axis as the first approximation to the root. Now equation of the chord joining the points an f of an and bn f of bn is the following: y minus f of bn divided by f of an minus f of bn equal to x minus bn divided by an minus bn. Let it be equation number 1. The point at which the chord touches the x-axis xn 0, and substituting this value in 1, we get the following: 0 minus f of bn divided by f of an minus f of bn equal to xn minus bn divided by an minus bn. This reduces to the following: c equal to an into f of bn minus bn into f of an divided by f of bn minus f of an, that is equal to determinant an bn f of an f of bn divided by f of bn minus f of an. This gives a first approximation to the root. If f of c equal to 0, c is the actual root. Otherwise, we continue our work until an approximate root of the desired accuracy is obtained. Algorithm for the method of false position. Given a function f of x continuous on an interval a0 b0 and satisfying f of a0 into f of b0 less than 0, for n equal to 0, 1, 2, etc. until termination, compute xn equal to determinant an bn f of an f of bn divided by f of bn minus f of an. If f of xn equal to 0, accept xn as a solution and stop, else continue. If f of an into f of xn less than 0, set an plus 1 equal to an and bn plus 1 equal to xn, else set an plus 1 equal to xn, bn plus 1 equal to bn. Then f of x equal to 0 for some x in an plus 1, bn plus 1. The rule of termination of the iteration is similar to those described for bisection method. Example 1. Using Regula Falsi method, find a real root of the equation f of x equal to x cube plus x minus 1 equal to 0 near x equal to 1. Solution. Here note that f of 0 equal to minus 1 and f of 1 equal to 1. Hence, f of 0 into f of 1 less than 0. So, by intermediate value theorem, a root lies in between 0 and 1. We search for that root by Regula Falsi method and we will get an approximate root. Step 1. Set a0 equal to 0 and b0 equal to 1. Then we have the following: x0 equal to determinant a0 b0 f of a0 f of b0 divided by f of b0 minus f of a0, that is equal to determinant 0 1 minus 1 1 divided by 1 minus minus 1, that is equal to 0.5, and f of x0 equal to f of 0.5, that is equal to minus 0.375. Step 2. Since f of 0 into f of 0.5 greater than 0, a root lies between 0.5 and 1. Set a1 equal to x0, that is equal to 0.5, and b1 equal to b0, that is equal to 1. Then we have the following: x1 equal to determinant a1 b1 f of a1 f of b1 divided by f of b1 minus f of a1, that is equal to determinant 0.51 minus 0.3751 divided by 1 minus minus 0.375, that is equal to 0.6364, and f of x1, that is f of 0.6364, that is equal to minus 0.1058. Step 3. Since f of 0.5 into f of x1 greater than 0, a root lies between x1 equal to 0.6364 and b1 equal to 1, and hence we set a2 equal to x1, that is equal to 0.6364, and b2 equal to b1, that is equal to 1. Then we have the following: x2 equal to determinant a2 b2 f of a2 f of b2 divided by f of b2 minus f of a2, that is equal to determinant 0.63641 minus 0.10581 divided by 1 minus 0.1058, that is equal to 0.6712, and f of x2, that is f of 0.6712, that is minus 0.0264. Step 4. Since f of 0.6712 into f of 0.6364 greater than 0, a root lies between 0.6712 and 1, and hence we set a3 equal to x2, that is equal to 0.6712, and b3 equal to b1, that is equal to 1. Then x3 equal to determinant a3 b3 f of a3 f of b3 divided by f of b3 minus f of a3, that is equal to determinant 0.6712 1 minus 0.02641 divided by 1 minus 0.0264, that is equal to 0.6796, and f of x3 equal to f of 0.6796, that is equal to minus 0.0063, which is approximately 0. Since f of 0.6796 approximately 0, we accept 0.6796 as an approximate solution of x cube minus x minus 1 equal to 0. This procedure is listed in the following table. Example 2. Given that the equation x raised to 2.2 equal to 69 has a root between 5 and 8, use the method of regular Falsi to determine it. Solution. Step 1. Let f of x equal to x raised to 2.2 minus 69. We find f of 5 equal to minus 34.50675846 and f of 8 equal to 28.00586026. x1 equal to determinant 5 8 f of 5 f of 8 divided by f of 8 minus f of 5, that is equal to 6.655990062. Step 2. Now f of x1 equal to minus 4.275625415, and therefore f of 5 into f of x1 greater than 0, and hence the root lies between 6.65599062 and 8. Proceeding similarly, x2 equal to 6.83400179, x3 equal to 6.8506696553. We accept 6.8506696553 as an approximate root, since f of x3 is approximately 0 for a tolerance level 0.05. In this module, the numerical methods for solving an equation are introduced. Bisection method and the regular Falsi method of solving equations based on intermediate value theorem for continuous functions are discussed in detail. The ways of solving equations by these methods are illustrated. Before concluding the session, try to solve the following problems. Number 1. Solve the following equations using bisection method. 1. X cube equal to 5. 2. X cube minus 7x plus 9 equal to 0. Number 2. Use bisection method to solve the following equation correct to 3 decimal places. X cube minus x square minus x minus 3 equal to 0. Number 3. Find the real solution of the following equations by regular Falsi method. 1. X raised to 4 equal to 3. 2. X cube minus 3x plus 2 equal to 0. Number 4. Starting from the given x0 values, solve the following equations by regular Falsi method within 4 steps. Number 1. X cube minus 5x plus 3 equal to 0 for x0 equal to 2. X raised to 4 minus x cube minus 2x minus 34 equal to 0 for x0 equal to 3. The books for your reference are C. E. Froberg, Introduction to Numerical Analysis, 2nd edition, Addison Wesley, 1979. James B. Scarborough, Numerical Mathematical Analysis, Oxford and IBH Publishing Company Private Limited, 1966. M.K. Jain, S.R.K. Iyengar, R.K. Jain, Numerical Methods, Problems and Solutions, New Age International Private Limited, 1996. M.K. Jain, S.R.K. Iyengar, R.K. Jain, Numerical Methods for Scientific and Engineering Computation, New Age International Private Limited, 1999.